So now that we have looked at the alkanes and alkenes and alkynes, we move on and start looking at ringed structures. So ring structures are very, very common everywhere in chemistry. There's a lot of reasons. Generally, they're more compact. It creates relatively nonpolar regions. It's flexible. It kind of keeps the shape of the molecule easy to adapt and easy to sort of fit in certain spots. Ring structures are generally quite stable as well, which also gives them a huge benefit. So these are going to be called your cyclic compounds. And there's really two types we're going to look at. We're going to look at cycloalkanes and alkenes, and then we're also going to look at some aromatic compounds, which are compounds based on benzene. Two very common ringed structures that we have here would be testosterone, which is a sex hormone that everybody has, and then cortisol, which is the stress hormone, which, again, are two examples of molecules that completely control your body in various ways. And a lot of these compounds will come up as you continue to study chemistry and as well biology. So that takes us down to sort of naming and drawing, which is really where support is usually needed. To draw a structure of cyclic hydrocarbons, we use a line diagram simply in a ringed shape. The biggest difference is that a cyclic alkane compound has a generic formula exactly the same as a straight chain alkene. That is because the two hydrogens at the end will be lost, so those two ends can circle around and connect to each other. Numbering becomes relatively meaningless when it's just an alkane, and numbering, of course, changes a little bit based on where the branches are and what other functional groups may be present. So when we look at this particular process as to how we go from a straight chain alkene like hexane to cyclohexane, it's relatively straightforward. So the first thing that needs to happen is the ends have to lose their hydrogens. So basically, we can lose a molecule of hydrogen or two hydrogen ions. It really depends on exactly what the reaction conditions are. And that leaves us to exactly the same molecule we had, except there is no third hydrogen on the end. And those two ends, just like two ends of a magnet, will circle around and find each other and form a ring structure. Where I'm just going to kind of highlight where that potentially would have connected. And of course the hydrogens for the complete structural diagram would still all be there. It's going to get really crowded in the center here. This is obviously really confusing to draw, so normally we just draw a line structure for it, where again each vertice is a carbon atom. And this is hexane as well, but it's called cyclohexane. So you'll notice the biggest difference between hexane and cyclohexane, other than a structure, would be that the hydrogens follow a different pattern. There's two less hydrogens in the overall structure. So the naming is very straightforward because we just take the structure and we look and we name the longest chain. And if there's no branches, we really don't even need to number it. We add the prefix cyclo to it. So this is a 1, 2, 3, 4, 5. So it's pentane. And to show that it's in a ring structure, we write cyclo out in front. And that basically is the biggest part about this. There are obviously a couple conditions that have to be met when we have branching taking place. So when we look at molecules like this, where we have a branch, we always start numbering from where the branch is. It's the same rule we've always been using. Give the branches the lowest possible number. And there's no other functional groups here. It's still just carbon and hydrogen. In a situation like this, we have a branch, which is a methyl group, and then we write our cyclohexane. So it's 6 carbons. That's the hexane. Cyclo because it's in a ring. You don't have to put 1-methyl cyclohexane because it would be implied, because there could be no other possible numbering sequence that would be allowed, because methyl's always going to get 1 if it's the only thing present. When we look at rings with 2 branches, we always give the lowest number to both of them, and the one that's going to get the 1 will be the one that comes first alphabetically. So we're going to go counterclockwise here. So in this case, we'll use both of our numbers. It'll be 1-ethyl, 3-methyl, cyclohexane. Remember that hyphens only separate numbers from letters, and commas separate numbers from other numbers, but letters next to letters don't have anything in between them. When there is a double bond present, so this is a cycloalkene, we always start numbering at the double bond, because the alkene group would have a higher priority. So we start numbering, and we want to give the branch the lowest number, so 1, 2, 3, 4, 5, 6. So your numbers need to include both parts of that double bond. So it's pretty much the same as we've been doing. 3-methyl, cyclohex. Now we write ENE. There is no need for a number in this case, because by definition of what we've been doing, that has to be position 1. So you could, if you wrote 1 cyclohexene, it's really not needed information. So you have a couple here to try, so you should pause the video and take a second to try them as you go through, and then play to see how you did. So with this group, this is our ethyl and this is our methyl. So ethyl comes first alphabetically. So we number this way, and we name this 1-ethyl, 3-methyl, cyclopentane. For this one, 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4. Tetramethyl for the 4 methyl groups. Cyclohexane, remember you got to get that word cyclo in there. This one is a cyclic compound with only 1 methyl group, so all I have to write is methyl cyclobutane. Again, no double bonds, it's 4 carbons, so that's where the bute comes from. So that takes us to our second type of cyclic compounds, which is the aromatics. Aromatic compounds are basically the alternative to aliphatic compounds from what we've been doing. It is simply a group that is based on benzene. The formula for benzene is C6H6. It is very, very, very stable. It was once used very commonly as an organic solvent. It is a carcinogen though, so it's a lot less common than it used to be. Basically what benzene is it is a cyclic 6-carbon ring where there is alternating double bonds, and these double bonds will move back and forth in resonance. So the more common way that we write it would be just with a circle to represent that resonance, and for a line diagram, it's just that structure there. Anything that has that 6-membered ring with the circle inside, or even 3 double bonds drawn like that, is benzene and would be considered aromatic. It's so common that there are some very common benzene groups. So for example, this one is methylbenzene, is going to be called toluene. An ethene group attached to a benzene is called styrene, which you'd be familiar with. Trinitro, 1, 2, 3, and again, toluene is the root, would be your TNT. So basically how we go through and we name these is very similar to what we do with our cyclic groups. It's just, there's just a couple little particularities about it. You still name the ring starting with the number on the lowest branch. You still name it with, if there's a functional group present, you start numbering at that functional group. So the lowest priority would be a methyl group, ethyl, and then propyl, etc. Then any of the halogens, then an amine group or a nitrogen group, and this is a hydroxy group or an alcohol group. So this would be where it would get number 1. If that wasn't present, then this would, etc. as you go down the list. A lot of benzene rings have 2 groups on them. So what that does for us is, let's just draw a bigger ring here. And let's put a methyl group here. Let's make it toluene. So we have 3 groups to the right of this, 3 positions. So we write ortho, meta, and para. And on the other side, we also have ortho and meta. It's the same word on both sides. So ortho means next to that group, meta means 2 away, and para means opposite. So if I'm naming these particular groups that are here, again, this is just to cut down on the use of numbers. This would be ortho, or just O, ortho dimethylbenzene. Or again, we could just write O. Dimethylbenzene. This one here, this OMP, would be meta dimethylbenzene. And this one would be para dimethylbenzene. Again, we just use these as position numbers. It tells you relative where the 2 groups are relative to each other. But you're going to find the naming of these groups very, very similar to what we have done. So here's some examples. So here's, once again, it's alternating double bonds, which again could be replaced by a circle. There's a couple different ways you could name this. So the common one would be ethyl. So 1, 2, 3, 4. We start with the ethyl group. So 1 ethyl, 4 methyl, benzene. You don't need the cyclo compound if it is benzene, because benzene is a ring by definition. We could also say that these are para to each other. So para ethyl methyl benzene would be another way to write this. Or this molecule here is called toluene, and you saw that on the previous page. So I could also write this para ethyl toluene, which again is a proper way to name it. Any of those 3 are fine. There's a lot of different ways you can look at things when you go to draw them. So when we go to draw these structures, again, it gets really quick because everything is based on that benzene ring. So 1 ethyl, 3 methyl benzene. So start with our benzene ring. So there's my ethyl group. 1, 2, 3. Put my methyl group in. That's it. Start with benzene. 1,4 dimethyl 2-ethyl. That's that one. Ortho diethylbenzene. Para-dichlorobenzene. We never really talked about chloros yet, but chloro just indicates the chlorine atom. As you can see, the use of P for para makes the name a little bit neater. It's the huge benefit. So finally, we have this group, this grouping of questions that sort of is mixed from everything we've done. So you should take a second and pause and go through and see how you do. So again, we've got to find the longest chain. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Again, it depends on how you do the long chain. 1, 2, 3, 4. 1, 2, 3. So for A, it would be ethyl first. 3 ethyl. 2, 4 dimethyl. Straight chain. Hexane. For B, we have a double bond present, and we know that we've got to include that double bond in our long chain. So 1, 2, 3, 1, 2, 3, 4, 5. Just the straight chain would work. We have 3 methyl groups, so 1, 2, 3, 4, 5. So I have methyl groups at 2, 4, 4, trimethyl, 1, pentene. Again, we got to indicate where that double bond is. For C, we know we have to include the triple bond that's there. So 1, 2, 3, 4, 5, 6. 1, 2, 4, 5, 6. 1, 2, 3, 4, 5, 6. I'm just going to use this chain. I have a propyl and an ethyl. So 1, 2, 3, 4, 5, 6. Give your triple bond the numbering priority. So 4 ethyl, 3 propyl, 1 hexane. For D, let's make sure we count our rings properly. It's a double bond, so we start numbering there and then go around so our branches get the right numbers. 1, 2, 3, 4, 5, 6. So 7. So we start 2 ethyl, 3, 4, 5, 6. Tetramethyl, cycloheptane, heptas in 7. I don't need to include the position number of the double bond because it would be defined as 1. This one is a lot easier. It just becomes ethyl for my ethyl group, ethyl benzene with the circle. So the big thing would be remembering that when you have a cyclic compound, not a benzene ring, you have to have that word cyclo in there. The numbering and the prefixes is more or less the same. And once you have benzene, there's a couple other rules that can apply.